Hey everyone, today I want to talk about the concept of the modulus and the argument of a complex number. So let's start with the modulus. The modulus of a complex number is essentially its distance from the origin. Or to put it more formally, let's let z equal x plus iy. So z is a complex number where x is the real part and y is the imaginary part. Then the modulus of z, and this is represented using the absolute value bars. And you can actually say absolute value instead of modulus, and these are synonymous terms for complex numbers. They mean the same thing. So if z is equal to x plus iy, then the modulus of z, or the absolute value of z, is equal to the square root of x squared plus y squared. And recall that x and y are the real and imaginary parts of z. So something I want you to notice here is that this is essentially just the Pythagorean theorem, right? Because if we substitute x and y out for the two non-hypotenuse sides of a right triangle, well, this is just precisely the formula that finds the distance, or sorry, not the distance, the length of the hypotenuse of the triangle. So let's go ahead and understand why the Pythagorean theorem is showing up in this definition. So let's go ahead and draw in our complex plane. We have the imaginary and the real axis. Okay, and let's draw in our arbitrary complex number z. So why is this Pythagorean theorem showing up? Well, notice that if we create a right triangle and connect the tip of the vector representing z to the real axis, well, the base of this right triangle is actually just x, or rather the length of the base of the triangle is x, or the real part of z, and the vertical side of the triangle is simply represented by the imaginary part of z, or y. So this is why the Pythagorean theorem is showing up, is because we're calculating the length of this vector here, or the distance from z to the origin, by creating a right triangle that corresponds to the real and imaginary parts of z. So that is why we find the Pythagorean theorem in the definition of the modulus, and that is how you find the modulus of a complex number. Now, before we move on to the argument, I want to go ahead and do a quick example of finding the modulus of a complex number, just to make sure that we understand the concept. So let's go ahead and say that we have a complex number 1 plus 3i, okay? And we want to go ahead and find the modulus of this number. So the modulus of z. Now recall, in order to do this, that we need to find the square of the real part and the square of the imaginary part first. So the real part of z is 1, and 1 squared is 1. So that's going to be the first term under the square root. And we want to add on to this the square of the imaginary part. So the imaginary part of z is 3, and 3 squared is 9. So this is the expression that's going to give us the modulus, the square root of 1 plus 9, which is equal to the square root of 10. So the square root of 10 is the modulus of z, and there's an example of finding the modulus. So now let's go ahead and move on to the concept of the argument of a complex number. And this topic is a little bit more complicated than the modulus, so just stick with me. And after I do the formal definition, I'm going to give a more intuitive explanation of what the argument is. So let's go ahead and start off by defining R to be the modulus of some complex number z, because we're going to go ahead and use this in our definition of the argument of z. So let's start by letting z equal x plus iy. So z again is a complex number where x and y are the real and imaginary parts. Then the argument of z is a number phi, and I'm just using phi here because phi is just a symbol that's typically used to represent an angle, which is exactly what the argument is. It's just an angle. So you could substitute this out for theta or something else, but typically in all the textbooks I've seen, they use phi. So the argument of z is a number phi, and phi is a real number such that we're going to go ahead and write our definition down here. So it's a real number phi such that x, or the real part of z, is equal to r cosine of phi, and the imaginary part of z, or y, is equal to r sine of phi. And this is the formal definition of the argument. And for those that may be new to this, this may not mean anything to you, and that's completely fine. Because right after this, I'm going to go ahead and give an intuitive explanation of what the argument is. So let's go ahead and do that. Let's go ahead and erase all of this, and then we're going to go ahead and draw in our complex plane. So let's get rid of this. Perfect. So let's draw in our imaginary axis and our real axis. All right, here's, oh, whoops, I botched that. There's RE, there's IM. Let me redraw that actually. RE, okay. And let's go and just throw in some units really quick. So here's 1 and 2. Let's say this is I right here. So let's say we have a complex number z, and let's set it equal to I for now. And we want to find the argument of z. Well, what exactly is the argument of z in an intuitive sense? Well, in an intuitive sense, the argument of z is the angle from the real axis to the vector representing z. So if we draw our vector really quick, it's just going to be a vertical line that ends at I. Well, the argument of z is simply this angle right here. It's the angle from the real axis to this vector. So this is phi. Now, notice that this angle is just 90 degrees, or pi over 2 radians. So that is the argument of z in this context, pi over 2 radians. So that is the argument of a complex number. Now, after this, it may be useful to, find some sort of formula for the argument, but that's going to be a little bit trickier in this case because the formula for the argument actually depends on which quadrant the complex number is located in. So for example, if I have some complex number in quadrant 1, which is this quadrant, well, we can simply use this formula. Let's label this, let's say, omega. So if we want to find the argument of omega, then that's going to be equal to the inverse tangent of y over x, where y is the imaginary part of omega and x is the real part of omega. And that's just basic trigonometry, right? We're using the inverse tangent to find this angle of this right triangle. So that's how we find the argument of a complex number if it's in quadrant 1. However, notice if we have some complex number in quadrant 2, well, this becomes a little bit trickier, right? Because if we use this same formula, we're going to be finding this angle right here, which is not what we want. We actually want the angle right here that connects to the real axis. So in quadrant 2, you're going to have to modify the formula a little bit. You're going to have to take 180 degrees, or pi radians, minus the angle that you get out of this computation. So depending on what quadrant you're in, you're going to have to do a little bit of modification to the angle because that's just the way that it works depending on the quadrant that your complex number is in. And that is the concept of the modulus and the argument of a complex number. And that's about it.